In this lecture, we're going to look at two important properties that a function may or may not satisfy. The first property is called the one-to-one or injective property. The one-to-one or injective property. Okay, a function f from x to y is said to be one-to-one when you don't have two elements in x that get sent to the same element in y. Okay. For example, consider this function. This is a one-to-one function because no two elements in x get sent to the same element in y. Okay, a gets sent to 2, b gets sent to 1, and c gets sent to 4. In contrast, look at this function. Okay, a gets sent to 2, b gets sent to 1, and c gets sent to 2. This is not a one-to-one function because a and c both get sent to 2. The formal definition of the one-to-one property is for all x1 and x2 in big X, if f of x1 equals f of x2, then x1 equals x2. Okay, let's do some examples. Let f from z to z be defined by f of n equals 2n. Show that f is one-to-one. Okay, suppose f of n1 equals f of n2 for arbitrary n1 and n2. In Z. Okay, well, by definition of f, we get 2n1 equals 2n2. Dividing out by 2 on both sides, we get n1 equals n2. Hence, by definition of one-to-one, f is one-to-one. Okay, now for the next example, let f from z to z be defined by f of n equals n squared. Show that f is not one-to-one. Okay, to show this, we just need two integers, n1 and n2, such that they both get sent to the same number. Okay, note that minus 2 squared is 4, and 2 squared is 4. Okay, so minus 2 and 2, they both get sent to 4. Hence, f is not one-to-one. We've seen that the one-to-one property requires that each element in the codomain has at most one element sent to it. The second important property we want to look at, the onto or surjective property, requires that each element in the codomain have at least one element in the domain sent to it. Okay, so this is the onto property, also called the surjective property. Okay, let me repeat that. So this property requires that each element in the codomain have at least one element in the domain sent to it. Okay, for example, consider this function. Okay, this function is onto because each element in y has some element in x being sent to it. In contrast, look at this function. This function is not onto because 3 doesn't have any element in x being sent to it. The formal definition of the onto property is for all y in big Y, there exists a little x in big X such that y equals f of x. Let's do some examples. Okay, let f from z to z be defined by f of n equals n plus 1. Show that f is onto. Okay, let m in z be an arbitrary integer. Okay, we need to show that there is an integer that gets sent to m. Okay, note that m minus 1 is an integer. And f of m minus 1 is m minus 1 plus 1. This is by definition of f. Now, simplifying this a little bit, I get m. Hence, there is an integer n such that f of n equals m. Thus, f is onto. Let's look at another example. Let f from z to z be defined by f of n equals 2n. Show that f is not onto. Okay, to show this, we just need one element in the codomain z that has nothing in the domain z sent to it. So let n be 3. Then there is no integer n such that f of n equals 3. Okay, suppose not. Then 3 equals f of n for some integer n. Okay, so 3 equals 2n. by definition of f. Okay, but that means that 3 is even. But 3 is not even, so we have a contradiction. Okay, so this original statement here that there is no integer n such that f of n equals to 3 is true. Okay, since we found an integer in the codomain that has nothing in the domain sent to it, f is not onto. Okay, so f is not onto. Note that we could have chosen any odd integer as our counterexample, since the range of f consists of only even integers. Okay, here we chose 3 as our counterexample. We could have chosen any odd integer.